Hey guys, I'm Parkin and I'm gonna react to this. This video about tornadoes, but disasters explained one. Okay, let's see.
We're talking about tornado shapes. Most people think a tornado is just a spinning cone that drops from the sky and tears things apart. But what if I told you there's a tornado 2.6 miles wide? A tornado that
That's Elvino.
grew into a monster in under 60 seconds? And one so thin it's barely visible, yet still ripping apart buildings. Today, I'm breaking down the most.
Okay, we are off to a bad start. Like, what do you mean? The dead man walking has legs. Okay. And it's called a nocturnal tornado, not called a night tornado.
Fascinating tornado shapes. The multi-vortex tornado.
It's
Now imagine
multi-vortex.
looking at a tornado and seeing multiple smaller tornadoes rotating inside it. Distinct funnels weaving around each other in chaotic, unpredictable patterns. Multi-vortex tornadoes contain two or more suction vortices that orbit within the main circulation. Each suction vortex has its own intense
Bro, that's a dead man walking tornado. Oh, we gotta be kidding me now, bro.
rotation, layered on top of the parent tornado's rotation, creating localized wind speeds far higher than the broader storm. This creates damage patterns that look random. One house is completely erased, while the house next door is nearly untouched. The spacing between suction vortices can be 50 to even several hundred feet. As the tornado moves, the vortices rotate around the center, creating multiple damage tracks that weave in and out. Suction vortices appear and disappear rapidly. The parent tornado might exist for 30 minutes, but individual suction vortices might last only 30 seconds before dissipating and being replaced by new ones. Radar might show one circulation, but on the ground, there are 3, 4, 5 distinct funnels. For anyone sheltering, this is uniquely dangerous. You might survive the initial impact, only to have a suction vortex pass overhead seconds later with catastrophic force. Your shelter might be rated for EF3 winds, but a suction vortex with EF5 winds can exceed those ratings. Twin tornado.
Because just like the Alvina, Oklahoma dead man walking the 2013 Alvina, Oklahoma EF3 dead man walking tornado. It's rated as EF3, but the multi-vortex are EF5. And now twin tornadoes.
Storm chasers were tracking a dangerous supercell over Nebraska in June 2014, when the storm produced two violent tornadoes simultaneously. Not one after the other, but at the same time. Two fully independent EF4 tornadoes, side by side, both packing winds over 200 miles per hour, carving parallel paths just a mile apart through the town of Pilger. Tornadoes form when a storm's rotation concentrates into a single dominant vortex. The atmosphere typically consolidates its energy into one circulation. But in rare cases, the storm environment becomes so unstable that the atmosphere refuses to pick one and creates both. You can see both funnels in the same frame, tearing through the landscape like predators hunting in tandem. Radar signatures become crowded and difficult to interpret. For those on the ground, escape routes vanish. If one blocks the road east and the other blocks the road west, where is safety? The rain-wrapped tornado. You're looking at heavy rain, thick gray curtains of precipitation moving toward you. Except hidden inside that rain is a tornado, and you won't see it until debris starts hitting your house. Rain-wrapped tornadoes occur when a tornado becomes completely embedded within the precipitation core of its parent storm. Heavy rain surrounds the vortex on all sides, creating an impenetrable visual barrier. The tornado could be EF3 intensity with 150 plus miles per hour winds, and from any angle all you see.
Actually, it's the advanced for this scale is measured by damage, not wind speed.
Is rain. Everything looks like a typical severe thunderstorm. See rain, hear thunder, maybe notice stronger winds. Your brain categorizes it as severe weather, but not immediate life-threatening emergency. There's no visual trigger, no funnel, no debris cloud to override your assumption that this is just heavy rain. By the time the sound of the wind becomes loud enough to distinguish from rain noise, the tornado might already be on top of you. And at that
What if that man had a tornado?
At that point, you've got seconds, not minutes, to take shelter. Even experienced storm chasers struggle with these. You can be positioned perfectly, staring directly at the storm, and see nothing but rain. Radar shows violent rotation, warnings are being issued, but visually, zero confirmation until debris starts flying. The night tornado.
Why was there an AI car?
Picture this. You're staring into pitch black darkness, knowing something
Nocturnal
massive is moving
tornado.
toward you. Then lightning strikes, and for half a second you see it. A wall of destruction. Then it's gone. Complete darkness again. Night tornadoes aren't meteorologically different from daytime tornadoes. Same rotating supercells, same wind shear, same atmospheric ingredients. The terror is purely sensory. After dark, there's no sunlight to reveal the condensation funnel. No contrast against the sky. No visual warning system your brain can process. Lightning becomes your only source of information. Brief, irregular flashes that show you snapshots of a tornado that might be a mile away or right on top of you. In that fraction of a second, you're trying to determine size, direction, speed, and whether you need to run. The human brain isn't built to process threats this way. We rely on continuous visual input to assess danger and make decisions. When that input becomes fragmented, our ability to judge distance and speed breaks down completely. What looked a mile away in one flash might be 200 yards closer in the next. And unlike rare variations we'll cover, this happens constantly. Tornadoes don't stop forming just because the sun goes down. Nocturnal tornadoes account for a disproportionate number of fatalities precisely because of the visibility issue. People are asleep, warnings go unheard, and even those who are awake can't see the threat approaching. Satellite tornadoes.
Oh, you got to be kidding
สุก
me.
อุ่นๆมาประคบถูๆเดี๋ยวก็หาย
Satellite tornadoes. During the most intense tornado outbreaks, a single funnel may not be the only danger. Satellite tornadoes appear as smaller, independent vortices that form near a much larger tornado, moving around it in a loose orbit-like pattern. Satellite tornadoes develop within the same storm system as the primary tornado, drawing energy from the broader rotating circulation. While the main tornado dominates attention with its size, these secondary funnels spin up quickly in nearby areas where wind shear briefly intensifies. Their paths curve, loop, or shift direction as they interact with the airflow surrounding the larger vortex. Most remain relatively small and short-lived with narrow damage paths. But their wind speeds can still destroy homes and flip vehicles. The real danger, how easily they escape notice. Radar displays highlight the dominant circulation, while the satellite tornado's weaker signature blends into surrounding storm noise. People focused on tracking the main tornado may assume danger is confined to one location, only to be struck from an unexpected direction. Post-storm surveys frequently reveal damage patterns disconnected from the primary tornado, later traced back to a satellite circulation that no one saw coming. The anticyclonic tornado. Every tornado in the northern hemisphere spins counterclockwise.
Yeah.
This is fundamental
But sometimes an anti-cyclonic tornado spins clockwise.
meteorology. Radar systems are calibrated for it. Storm spotters are trained to watch
Super,
for
they're
it.
super
It's the
weird
rule.
though.
Then, very rarely, a tornado spins clockwise, completely backward, and shatters every pattern we use to detect them. Anticyclonic tornadoes violate the dominant rotation direction. They don't form beneath the main updraft like typical tornadoes. Instead, they develop along the outer edges of supercells, where opposing wind boundaries collide and create reverse circulation. Most stay weak, but occasionally, when a supercell splits, the left-moving storm can develop a dominant anticyclonic mesocyclone. Storm spotters trained to identify counterclockwise rotation can watch an anticyclonic tornado approach without recognizing it. Your brain
How do you even recognize an anti-cyclonic tornado when it's already touched down?
sees motion that looks wrong somehow. You might hesitate.
All my storm chasing fans, can you explain this for me, please?
Doubt what you're seeing. Spend critical seconds trying to reconcile the visual with your expectations. Visually, you cannot tell the difference from a still image. The only distinction is rotational direction, and unless you're close enough to observe individual debris movement, you'll never know which way it's spinning. The Mount Everest region tornado. Quick question. Where's the last place on Earth you'd expect a tornado to form?
Thailand.
If you said the highest mountain range on the planet, you'd be right, and you'd also be wrong. Researchers documented a tornado forming in the Everest region of the Himalayas at extreme altitude, an event that shouldn't exist. Tornadoes need warm, moist air colliding with cooler air. They need atmospheric instability and enough air density to sustain rotation. The Himalayas have almost none of that. The air is thin, freezing, and bone dry. So, how did it happen? During the monsoon season, warm, moisture-laden air from the Indian Ocean gets pushed up the southern slopes of the Himalayas. As this air rises rapidly, it cools and collides with the frigid mountain air above. In rare cases, if the wind shear is just right and the updraft strong enough, this collision can create a rotating column, even at altitudes where tornadic activity should be impossible. What researchers witnessed was a funnel cloud forming and touching down in terrain where the atmospheric conditions were borderline hostile to tornado development. It was weak compared to plains tornadoes, but the fact that it existed at all broke fundamental assumptions. The wedge tornado.
Everyone knows what a wedge tornado is. Here's the thing about wedge tornadoes. It must be wider than its tallness. That's it. That's what I'm going to say. That's it.
Tornadoes don't look like funnels at all. They're so wide they appear as massive walls of churning cloud connected to the ground, often wider than they are tall. Some even exceed a mile in width.
I just said
Entire towns can fit within the damage path. But here's the deadly illusion. They appear to move in slow motion. Wedge tornadoes move at the same forward speed as traditional tornadoes, typically 30 to 50 miles per hour. Because they're so massive, your brain can't process the movement properly. They look like they're barely creeping forward, almost stationary.
Such as the 2013 El Oklahoma EF3 Deadman Walking Tornado. It is about 5 miles per hour. But that could be just fake news because how big it is. 2.6. About 2.6 miles.
By the time you realize the wedge is far closer than it was 2 minutes ago, it's too late to evacuate. You've wasted critical escape time standing there watching, convinced you had more time because it looked so slow. The invisible tornado. There's no funnel, no condensation cloud, no visible tornado. Just destruction appearing out of nowhere. Invisible tornadoes form when atmospheric humidity is too low for moisture to condense into a visible funnel, or when the vortex exists primarily at ground level, without extending visibly upward into the cloud base. The rotation is absolutely real, but there's nothing for your eyes to lock onto. Think about what a tornado actually is. It's a rapidly rotating column of air. The visible funnel we associate with tornadoes is just water vapor condensing inside that rotating column. But if the air is too dry, the rotation still exists. You just can't see it. Storm spotters have reported experiences that sound almost supernatural. Objects start flying, structures start coming apart, and there's nothing visible causing it. Doppler radar detects...
Well, I can kind of see the tornado. Just a little dust.
It's measuring wind...
Looks like a dust devil.
...speeds and rotation directly, not moisture. But if you're depending on your eyes, the tornado is already hitting you before you realize a tornado exists. The waterspout tornado.
Oh, you got to be kidding me. I hate your modern warships.
The waterspout tornado. Coastal communities see
The Southeast Asian tornadoes. Super weak. A standard car could intercept a waterspout.
Waterspout forming offshore and think, it's over the ocean, we're safe. That assumption kills people. There are two types of waterspouts. Fair weather waterspouts are generally weak and short-lived, but tornadic waterspouts are real tornadoes, generated by supercell thunderstorms that happen to form over water. Same rotating mesocyclone, same violent updraft, and the same destructive potential. When a tornadic waterspout crosses a coastline, it doesn't weaken, it often intensifies. Over water, the smooth surface reduces friction. But when that vortex moves over land, over beaches, buildings, trees, uneven terrain, the increased surface friction can tighten the rotation, accelerating wind speeds. The waterspout that looked peaceful over the ocean is now a tornado moving inland at 40 miles per hour and getting stronger. Tornadic waterspouts can sustain themselves for miles after landfall, crossing beaches and moving through coastal towns. And because they don't always produce classic radar signatures, Warnings can be delayed or absent entirely. By the time people realize it's not just a water spout, it's already causing damage.
Yeah.
The dead man walking.
You already said put a dead man walking. It's the Zero Texas. And the first one, the multi-vortex.
There's a tornado formation so visually
Zero.
disturbing that storm chasers gave it a name that sends chills down your spine. The dead man walking.
Why didn't you show the 2013 El Reno, Oklahoma, the EF3 dead man walking?
A tornado develops with a main funnel accompanied by two smaller vortices or debris columns positioned on either side, creating a silhouette that looks like a giant human figure striding across the landscape. The main funnel forms the body, while the flanking features create legs. The most famous documented example went viral not because of the destruction it caused, but because of how it looked. The silhouette was so clear that even people who'd never seen a tornado
That is literally freaking AI.
immediately understood the name. You could see the head, the torso, the legs. One storm chaser who witnessed it.
I can only see the size, the legs, and the torso of Zero.
I've been chasing for 15 years. I've seen wedges. I've seen multi-vortex monsters. But this was different. It didn't feel like I was watching a storm anymore. It felt like something was walking across that field with purpose. The dead man walking structure typically involves multiple vortices positioned in just the right alignment from the right viewing angle. There's no scientific evidence this visual structure predicts intensity. But what it does is break the psychological barrier between weather phenomenon and thing that looks like it has intent. The fire tornado. Forget everything you know about tornado formation. Forget thunderstorms, moisture, atmospheric instability.
This is just another Titan. Why are there so many Titans? Into the storm references.
Cold fronts. Fire tornadoes need none of that. Just heat, wind, and fuel. When extreme wildfires generate intense heat, with temperatures exceeding 2,000 degrees Fahrenheit, the superheated air rises rapidly in powerful updrafts. Surrounding winds and terrain introduce rotation into that rising column. When the rotation tightens, a vortex forms, pulling flame, burning debris, and ash into a spinning column of fire that can reach over 100 miles per hour. These aren't small fire whirls. We're talking about tornadic vortices with EF scale intensity. They melt paint off cars, warp metal, and lift vehicles and hurl them hundreds of feet. The sound is described as a mechanical roar like a jet engine screaming. You can't see them coming on Doppler radar. Weather radar looks for precipitation and measures wind speeds within storm clouds. Fire tornadoes have neither.
And first of all, it's not called the Doppler radar. It's called the Doppler on wheels.
The Carr Fire in California generated the first fire tornado ever to receive an EF rating, EF3 intensity.
Bruh.
It killed a firefighter and a civilian. It destroyed over 1,000 structures. Firefighters describe them as the most terrifying thing they've encountered. You're already fighting a wildfire, extreme heat, zero visibility from smoke, unpredictable behavior. Then the fire itself starts spinning, generating winds strong enough to flip fire trucks, and you realize you're not just fighting fire anymore. High-altitude tornadoes. Most tornado research focuses on flat, low-lying terrain where warm, dense air fuels powerful storms. But on July 7, 2004, a hiker photographed a tornado at Sequoia National Park's Rockwell Pass at 12,000 feet, the highest confirmed tornado in U.S. history. At extreme elevations, reduced air density affects how funnels appear. They look narrower, more transparent, sometimes barely visible as moisture struggles to condense. Despite their faint appearance, rotation near the ground can still cause damage. Mountainous terrain creates localized zones of rotation and turbulence that feed developing storms. Air flowing over ridges and valleys can cause small-scale circulations to intensify rapidly, sometimes producing tornadoes with almost no visual warning. The funnel photographed at Rockwell Pass was thin, barely visible, and shouldn't have existed according to traditional tornado science. If tornadoes can form where the air is too thin to support them, are there any environments where tornadoes truly can't happen? Volcanic tornadoes. When a volcano erupts, towering plumes of superheated gas and debris surge upward with tremendous force. Under the right conditions, these rising columns begin to rotate, creating volcanic tornadoes born inside eruption clouds. As scorching gases and ash rocket skyward from the volcanic vent,
That is
intense
not
turbulence develops. As the plume expands, pockets of rotation
okay.
tighten, pulling ash, rock fragments, and steam into a spinning column
Why
composed entirely of volcanic material. Ash hot enough to melt
Okay.
metal, rock fragments at hurricane speeds, and superheated gases. Electrical activity within eruption plumes can generate lightning without warning. You're looking at a rotating column of fire and ash that can strike you with lightning while tearing across the
Oh
landscape.
no. Oh, you got to be kidding me. I hate this.
Across the landscape. During the 2018 Kilauea eruption in Hawaii, fissure eruptions created lava nados, whirling columns of fire and ash spinning across lava fields with a roar that combined wind and fire. Volcanic tornadoes remain poorly studied because eruptions are impossibly dangerous to approach. But they prove rotation can develop in environments that have nothing to do with traditional weather. Snow tornadoes. In January 2013, a winter tornado struck near Shelburne, Ontario, packing 90 miles per hour winds, EF1 intensity. It destroyed a farm silo and damaged a barn, proving tornadoes can form even in freezing temperatures during blizzards. Snow tornadoes, also called winter waterspouts, emerge when very cold air moves over comparatively warmer surfaces, specifically large bodies of open water like the Great Lakes. This temperature contrast creates just enough instability for rising air to organize. When wind shear is present, that rising air can rotate, tightening into a visible funnel. In snowy environments, the vortex lifts loose snow and ice crystals, creating a ghostly translucent column, nearly invisible until it's nearby. Low visibility, falling snow, and limited daylight make them exceptionally difficult to spot. Most remain weak and short-lived, but these events fall completely outside typical tornado season, catching both the public and forecasters by surprise. Nobody's watching for tornadoes in January. Nobody's thinking about shelter when it's snowing. Needle tornadoes. Imagine you're driving and you see something strange. A thin line hanging from the sky like someone drew a single stroke with a marker. It's so narrow you're not even sure it's real. Would you stop? Would you take shelter? Or would you assume it's harmless? That decision is crucial and could even kill you. These are needle tornadoes, sometimes no wider than a telephone pole. They form in the earliest stages when rotation is tight but starved of moisture. They can appear and vanish in seconds, carving quick scratch marks before dissolving like smoke. But can this really be dangerous? The answer is yes. Needle tornadoes can pack winds exceeding 80 or 90 miles per hour, strong enough to flip structures and send debris tumbling. They're nature's first whisper before the scream. In 2016, storm chasers documented a needle tornado near Campo, Colorado, that was barely visible against the sky, lasted less than a minute but still managed to damage farm equipment. So, if something that looks like a thread can cause real damage, what happens when that thread starts moving, twisting and lashing like it's alive? The rope tornado. Picture a ribbon hanging from the cloud, swaying gracefully like it's dancing in the wind. Beautiful.
Let me guess, he's gonna say, Railway structure or serious harmless. Dude,
It's fluid motion.
it's dangerous.
Then it touches down and rips a barn apart in under 5 seconds. Rope tornadoes look fragile. They often form during a tornado's dissipating phase as the vortex contracts. The visual appearance screams weak to anyone watching. But thin doesn't mean weak. It means concentrated. When rotational energy compresses into a narrow column, sometimes only 50 to 100 feet wide, wind speeds can spike dramatically. Conservation of angular momentum. As the radius decreases, rotational velocity increases. Rope tornado can generate EF2 or EF3 winds in an extremely focused area. Storm chasers describe them as deceptively beautiful, mesmerizing, photogenic, almost hypnotic. It's easy to get captivated by the visual beauty and forget you're watching something capable of extreme violence. Elephant trunk tornadoes. Picture a funnel that widens toward the ground, looking like an elephant's trunk reaching from the sky. Unlike the unpredictable rope, this one moves with purpose. So what does that widening mean? Is it getting stronger? Is this the moment you need to run? The answer is maybe. Elephant trunk grow stronger, pulling in more moisture and debris. They often mark the trajectory of weak tornadoes and powerful ones. You're watching something become dangerous in real time. Storm chasers love them because they're dramatic without the overwhelming width of larger tornadoes. But don't let that grace fool you. they can still reach EF2, strength or higher. The Simla, Colorado tornado of June 2015 became one of the most photographed elephant trunk tornadoes in history. Storm chasers captured it leaning and curving across the plains in a perfect elephant trunk shape, which eventually caused significant damage to rural structures. As the elephant trunk tornado thickens and stabilizes, the classic tornado shape emerges. And that's when the real danger starts. Cone tornadoes. If you were asked to draw a tornado, you'd sketch a cone. Wide at the cloud base, narrow at the bottom. It's the textbook shape everyone recognizes. But here's what most don't realize. If you're looking at a cone, you're not watching the beginning. You're watching a tornado that has decided to strengthen. Cones form when rotation intensifies, pulling in massive amounts of warm, moist air. This thickens the funnel into a tapered triangle ranging from barely wider than a house to hundreds of yards across. Cones are stable, long-lasting, and capable of intensifying without warning. Many EF3 and EF4 tornadoes start as cones before morphing into something bigger. An example is the Tuscaloosa-Birmingham tornado of April 2011, which spent much of its deadly 80-mile path as a massive cone tornado. Witnesses described it as a perfect dark triangle cutting through neighborhoods, eventually reaching EF4 intensity and killing 64 people. Hourglass tornadoes.
Hourglass.
Imagine watching a tornado that looks
Fun fact, in Dust Tornadoes 1, EF4s are often like hourglass.
squeezed in the middle, like invisible hands pinched it. The top is wide, the bottom is wide, but the center, impossibly narrow. So how does that even happen? How does a tornado stay connected when the middle looks ready to snap? Hourglasses form when strong inflow near the ground and powerful rotational lift overpower the mid-level inflow, tightening the funnel in the center while both ends expand. The result is so unusual that even experienced chasers do double takes. The Ray, Colorado tornado of May 2016 became one of the most documented hourglass tornadoes ever. Both the top and bottom of the tornado can contain violent winds capable of serious damage, and some hourglasses have rapidly expanded into wedges that doubled in size within minutes. This shape reminds us that tornadoes are fluid, constantly evolving. They transform in real time, sometimes faster than you can react. Stovepipe tornadoes. If a cone looks dangerous, a stovepipe looks like a declaration of war. Perfectly vertical, uniformly wide, and ominously dark. The stovepipe is one of the clearest signals that a storm has developed serious, sustained rotation. And it's not stopping. This stovepipe isn't wobbling or weakening, it's locked in. Stovepipes form when the tornado pulls in so much moisture and debris that the funnel becomes solid and sharply outlined. Many high-end EF3 and EF4 tornadoes hold this shape for miles, carving brutal paths. The Andover, Kansas tornado of April 2022 was such a classical stovepipe. It maintained that shape for an extended period as it moved through the town, causing EF3 damage and destroying dozens of homes. So, which tornado shape shocked you the most? Drop your comment below. And if you'd like to see...
So that's it. Shout out to Disasters Explained 1. So that's it. Bye-bye.